Okay, guys, can you guys hear me? Okay, perfect. Just give me 1 sec. Just give me 1 sec. And there's a connection issue for my HDMI cable. Let me make sure it comes to here. Okay, all good. Okay, I'm just gonna drag it here. Make sure it's frozen. Now you guys still hear me, right? It's good. The audio?
No, I can hear you.
Okay, perfect. So let's get started. I'm gonna share my screen here. Give me a sec. Yeah, you should be able to see my screen right now. All right, so let's get started. And this is like the second lecture of our mathematical thought lectures, right? In the last lecture, we actually introduced pretty much a lot of information regarding the construction method, right? And what we focused in the last lecture is pretty much the algebra-related problems. We focus a lot of time working on the inequalities for something like the sequence, so on and so forth. So this is actually a very important part for the construction to kick in. So before we get started and go to today's lecture, let's have a look at our assignment first. Okay. So question number 1, let's do this one by one. Assignment review, question number 1. Okay, for question number 1, it says, yeah, I think in today's allocation is that question number 1, I'm going to be asking for Jennifer. Number 2 will be James. And number 3, I'll ask Joey. Okay, so let's get started. For number 1, it says you have 4 numbers, they're all positive numbers. Please determine the area of a triangle with the 3 sides. So for this question, I'm gonna ask Jennifer to give us some ideas.
Can you guys hear me?
Yep.
Okay, so you can observe that these 3 sides are all square roots. So so you could get a hint that you might be constructing some sort of square or right triangles from this. So from the sides of the triangle, you can construct a right triangle. So for example, the b squared plus c squared under square root, that would be b squared plus c squared. How do I put this? It's like the hypotenuse of the b squared and c squared side. And also for the others, for the a squared plus c squared plus d squared plus 2cd, you can separate them as a squared plus c plus d squared. It's just a factorization. And then you basically put this entire triangle into a rectangle. And you can just get the entire area of the rectangle and minus the 3 little, was it 4? 3?
Yep.
Yeah, the other areas.
Okay, perfect. Thank you, Jennifer. Yeah, I think for question number 1, pretty much everyone has the correct direction, right? Instead of doing the hard calculation, what you're going to do is doing a construction. Like we mentioned in the previous lecture, you're going to construct either a rectangle or like a triangle, so on and so forth. Try to make sure all your conditions can be fit in, right? I'm just going to write it here. So you're going to be D, C, B, A, right? So B, C, D, A, right? As long as you create such a rectangle with all the sizes, you'll be able to find that these are actually the 3 sides of this triangle. If you want to calculate the area, instead of using the Heron's formula, what you're going to do is using the big area of the rectangle minus the 3 right triangles, and you get what you need. All right, this is for question number 1. Question number 2 is here. Question number 2, actually, it's a very interesting question. I really like to spend a little bit time talking about the the method, how we're going to do this problem moving forward. I think for this problem, I'm going to ask James to give us a more, what should I say, more standard solution, more direct solution. And also, Alan has a totally different solution as well. And his solution is very good. He's actually using the Lagrange stuff. So Norris, let's get started from the James solution first. Hey, James, you hear us?
Oh, yeah, okay. Can you guys hear me?
Yeah, I hear you.
Okay. So basically what I did is, well, first you have to notice that this should hold for any positive integer n. So what I basically did was I tried to simplify well, not simplify, but change each of these terms, a1 to the power 4 over a1 cubed plus a1 squared a2 plus a1 a2 squared plus a2 cubed into something where I could analyze the term itself and like say something about it. So right now we can't really say too much about it because a1 could be like 0 or something, and then because we don't know anything about a2. So what I did was I basically simplified it, and I could not simplify. I basically showed that if you replaced each of the a1 to the power of 4 with like a2 to the power 4 on the top, and then for the next term a2 to the power 4, if you replace that with a3 to the power of 4, and then so on, if you did that with every term, then the value would remain the same. So then I noticed that if you double this entire thing on the left hand side, it's actually equal to a1 to the power 4 plus a2 to the power 4 in the top, and then a1 cubed plus a1 squared a2 plus a1 a2 squared plus a2 cubed in the bottom, right?
Mm-hmm.
So now that we have something like this, we can actually analyze something special about this. And if you do some AMGM and a bunch of manipulation, you can actually find that this complex term is actually greater than or equal to a1 plus a2 over 4. And then for each term, in general, if you have a to the power 4 plus b to the power 4 over a cubed plus a squared b plus ab squared plus b cubed, this is always greater than or equal to a plus b over 4. And then after you've simplified all that, you can just plug in a1 plus a2 all the way to an is equal to 1. And you get that it's actually greater than or equal to 1/2. And we initially started with double the left-hand side. So if you just divide both sides by 2, then you just get the inequality.
Okay, perfect. Thank you, James. Yeah, James' solution is basically using the AMGM, and I think it's pretty standard solution. And also, Alan has a fantastic solution for this problem. Maybe we're going to ask Alan to give us some ideas. He's using something more high-techy.
So for mine, basically, it's something from calculus called the Lagrange multipliers, which basically says that if you want to like have this function that you want to find the minimum or maximum values of, so you want to minimize or maximize something under a constraint. So the constraint right now is that the sum of all like a1 all the way to an is equal to 1. That's the constraint, and we want to minimize in this case this weird looking function over here. So basically, what it says is that like I suppose this won't be like very make a lot of sense for like if you don't know calculus, but it means like if you take the gradient of the constraint, it should be equal to the gradient of the function that you're supposed to like minimize or maximize up to some kind of constant like a Lagrange multiplier. And then basically, since we know that when we take the gradient of the constraint, everything's just going to be equal to 1. Because if you take the derivative of a1 with respect to a1, it's just going to be 1. So the basically like the vector that you get once you take the gradient, it's all going to be 1 because it's cyclic, and also because it's symmetrical, so they're all going to be 1. And then if we take a look at the gradient of the function itself, that's also cyclic. So when we take the gradient of it, we're going to have a bunch of different functions of a1, a2, and a3 all the way to an, but they're all actually going to be the same function, because the entire like thing is cyclic. So like you can kind of say like without loss of generality of any of them. And then basically, since everything's basically the same and they're all equal to lambda, the constant that we were using, we can tell that minimum is achieved when all the terms are going to be equal. So when all the terms are equal, obviously each of them are equal to 1 over n. And if you just plug in 1 over n into each of these things, you get 4 over n for each of the terms, and there's n terms. So that just comes out to 1/4. That's the minimum.
Yeah, exactly. So Alan's solution is from the calculus, and I think it's actually a very good solution, right? You don't really have to dig into too much the construction. You just directly, implement the Lagrange. You should be able just to make it work. Okay. So my solution is a little bit different, and I want to give you guys more the generic solution for this problem. Okay. The first of all, you want to see a quick observation for this, like 3, 4, 5, all the way to n different expressions. Your first reaction is that this is like a cyclic symmetric, right? You're basically replacing A1, A2 all the way, you go to AN. As long as you see the cyclic symmetric, the construction always gets started with something similar. We're going to also use the symmetric construction. Okay, this is actually something very important. You see something like symmetric, when you do the construction, you want to construct something symmetric. So how are you going to do the construction? How to make something symmetric? You see, let's say I'm just going to let this guy equals to A, right? This is the big thing. I want to say equal to A. I want to create something quite symmetric to A. So this is what I'm going to create. I'm going to keep everything the same as the denominator. Well, talking about symmetric, I want to do something a little bit symmetric, right? So what I'm going to do is I'm going to replace the A1 square equals to A1 to the power of 4 by using A2 to the power of 4, because these will make sure the first term of these two expressions are kind of symmetric. Is that right? So I'll do exactly the same thing. The second part, I'll change this into A3 to the power of 4. Keep the same denominator. All the way, the last one will be an cube, an square, a1, a1 square, a1 cube. This part, I'm going to put a1 to the power of 4, right? Instead of an to the power of 4. So these can make sure a and b are kind of symmetric, kind of comparable. Well, this is actually a very important conclusion. In most of this symmetric related construction problem, as long as you have two terms, a and b, most of the time, a and b together will have a very brief relationship. You're going to have either a equals to b, or a plus b equals to 0. This means a equals to minus b. But in our case, this is going to be impossible, right? Because we're all, oh yeah, I mean, like, yeah. So yeah, maybe not impossible. Like still, it is possible because a1 all the way to an, they have to be the positive integer. No, they don't have to be positive, guys. Or you might have something like a times b equals to 1, or something a squared plus b squared equals to 1. You're always going to find some very brief relationship between a and b. So this is the trend for most of the big problems. Okay. Actually, if you do a quick comparison for this, if I do a subtract b, I'm just going to give you one term as an example. A subtract b, okay? You're going to have the denominators exactly the same like this. And the numerator, just going to do this minus this, right? I'm going to do some quick factorization. I think this is not a magic, right? You guys should 100% understand. Right? And then I'm going to keep doing all the way to the last one. The last one will be exactly the same, but just put everything here and you'll be able to find it out. Okay, I'm going to do another quick analysis. I'm going to do a little bit rearrangement for this denominator as well. Just do some simple factorization, not a magic. Okay, I'm just going to write out the last term as well. Square an plus a1, an minus a1, and an square, a1 square, an plus a1. Okay? This can be cancelled. This can be cancelled. So the first term you have a1 minus a2. Second one will be a2 minus a3, right? All the way an minus a1. So that being said, a minus 1 equals to 0. It falls into one of our assumptions. A and B always have a very brief relationship. Okay, so that being said, A equals to B. Okay, if A equals to B, you know what? Let's have a quick look at this guy. Because A already equals to B, right? Let's have a look at here. Just the first term. Yeah, I know the first term might not be the same, right? Even though A equals to B, but not necessarily the first term are the same. But the first term might have some interesting properties that we can work on. If I add these first two terms together, you're going to have what? A1 to the power of 4, A2 to the power of 4, A1 square, A2 square, A1 plus A2, right? This is as I did before. Let's have a quick look. This guy I say will be equal to this, greater or equal to this guy. Do you guys agree with me? Do you guys agree with me?
Yeah.
Oh, good. Right? This is not a magic, right? Okay. So that being said, I'm just going to do another simplification. This guy will be equal to what? Right? Again, I'll say this guy equals to this guy, greater or equals to this guy. Is that right? Exactly. That these two inequalities are using exactly the same, like the same reasoning, right? Exactly the same reasoning. So that being said, actually equals to what? A1 plus A2 divided by 4. Is that right? Okay. So if that's the case, look at that. A equals to what? A and B, they're the same. It's actually equals to 1 over 2 A plus B. Is that right? And what I'm trying to do is that I have already found out, you see, the first two terms, adding them together is greater or equal to A1 plus A2 over 4. So if I put all the terms together, that one will be greater or equal to 1 over 2, 1 over 4, A1 plus A2, right? 1 over 4, A2 plus A3. All the way 1 over 4, AN plus A1. Is that right? You're just basically replacing every single term. This is not a magic, right? So what is that? That is actually A1 plus A2 all the way to AN, which is equal to 1. Is that right? So therefore, this guy will be equal to 1 over 4. Is that right? So like the beauty for this problem, I like to do a quick recap, is always, as long as you see a cyclic thing, try to do a construction using a similar cyclic pattern. Okay, for this thing, it's very understandable. You replace A1 square to the power of 4 by using A2 to the power of 4. Okay, and most of the time, whenever you do such a replacement, all those cyclic things will be always the same, or just like a reciprocal, or they just exactly the same for except for sign. There should be a very strong, like a very complicated relationship between these two guys. So this is the big trend. As long as you do this, you'll be able to figure out this problem fairly quick. Okay, this is our problem number 2. So far, so good?
Yes.
Oh, good. Let's go to question number 3. Question number 3 is a little bit difficult. And let's have a look how we're going to do question number 3. So it says that it's a Russian IMO pre-selection problem. It just defined a pretty weird expression or this under root thing. The question asks you to determine xn plus 1 minus xn is lesser than 1 over n factorial. So Joey, I'm gonna ask you, you don't have to do something super in detail because it's kind of like difficult to explain. Give us a big direction. It's good enough.
Okay. I actually think the most important thing about this problem is actually like the construction. So it's like you set the variable AI, which is equal to like you know how xn is from like 2 to n, right? So like root 2 of 2 plus cube root of 3 plus fourth root of 4. So you set AI like in that kind of like sense of pattern from I to n plus 1. So it'd be like ith root of I plus I plus 1 root of I plus 1 all the way to n plus 1. And then you set BI similarly, but except instead of from I to n plus 1, you set it from I to n. yeah, I'm kind of using a pattern here. So those are your two most important variables, AI and BI. And then once you realize that, you also have to set a CI. So because actually, firstly, it's really important to observe that AI to the power of I minus BI to the power of I is equal to AI plus 1 minus BI plus 1, right? And then you're just like, okay, so maybe we can induct here, right? And then this is where construction comes in. So then you realize, okay, so what do I have to multiply AI minus BI to make CI, to make AI plus 1 minus BI plus 1, right? So when you factorize your difference of squares, you usually get like x minus y, and then you get like this really complicated like factorization at the end, right? So we're just going to set that as CI, and the only thing we're going to note about that is that it has I terms. That's going to be pretty useful later on. Okay, so then you note that a2 squared, a2 minus b2 is actually xn plus 1 minus xn. So we're going to set, so we realize that this is actually pretty useful because you realize that if you go from a2 minus b2 and then you multiply that by a2 plus b2 or c2, right? And then you multiply that by c3, then you multiply that by c4, eventually you can actually peel away all of the roots, because every time we like raise ai to the power of I and then subtract that from bi, we just get ai plus 1 minus bi plus 1, what we found in the beginning. So in the end, what we get is an, so basically a2 minus b2 is equal to c2 a2 minus b2, which is what we want, multiplied by c2, c3, c4, c5, all the way to cn, is actually equal to an minus bn. Okay, so what does this tell us? So this is the second part. So notice how I told you that you have to keep in mind how many terms Cn had, right? Cn has n terms. And it's actually pretty important to notice that AI is always larger than 1. And this is pretty easy to trivially prove, because I is obviously larger than 1 and ith root. If you root anything that's larger than 1, no matter how many times you like root it, it's always going to be larger than 1. So that means Cn is always larger than n. So then that's where our n factorial comes in, right? Because you realize that Cn is always larger than n. So if you divide the right-hand side, because we had like this really weird expression, and that's actually less than 1, right? Like it's pretty easy to see that's less than 1 because you're rooting it so many times. It's probably going to be less than 1, right? That's probably not very rigorous, but like, I mean, the rigorous proof is probably pretty trivial. And then you divide the right side by C2, C3, C4, all the way to Cn. And then that's your, and that's going to be less. So then your right side obviously is going to be less than 1 over n factorial. So then therefore you proved your thing, because b2 minus a2, which is the only thing that's left on the left side, is what you want. So you get b2 minus a2 is actually less than 1 over n factorial.
Yeah, exactly. Yeah, this is a crazy problem. Also, Alan's solution is also correct, but it's totally using something totally different. Okay, so I'm going to give my solution to this. You know, for this problem, it's not necessary you understand every single step. You understand the big trend. It's good enough. How they do the construction. They actually do the very weird construction to make it happen, because it's very different. How do you create all those like under root thing, right? It is kind of like difficult for us to use the regular way to create it. Then in order to create such a form, you have to create another weird construction, and then using the relationship between these two things to make it happen. You can just have a quick look. This problem, you know what? The first reaction whenever you see this problem should be that you kind of have a telescope sequence, right? Because xn plus 1 minus xn, you know, this really gives a feeling, right? There might be some telescope-related stuff. So therefore, some terms might be canceled out, so on and so forth. Like I keep saying, all those constructions are based on the similarity. If you totally have no idea what this kind of expression is similar to anything, you might be very difficult to find out a way to do the construction. Right, so this problem, this is very difficult. Let me just try to give you the explanation, like the official solution, and let's try to understand how this official solution works. All right, so probably, as you can see that whenever you see such a big number, let's just try to do a verification for the lower numbers, for 2 or 3. Just have a look to see if this one works, right? So this is quite understandable. I'm going to change the color. Proof. So when n is equal to 2, right, you're going to find basically x3 minus x2. That one is easy. You can just basically plug in the value. It's under root 2 plus, I think it's under cube 3, which is, and then minus under root 2, right? That one is actually lesser than 1 over 2 factorial. So it's not a big deal whatsoever. Well, the $1 million question is that how can I prove something, whatever, greater than 2, right? So this is the part I need to do the construction. I need to construct actually 3 different sequences to make sure this expression can be held. So when n is greater or equal to 3, I need to construct 3 sequences. I call them AI, BI, CI. Okay, so how does AI looks? AI looks quite similar to our original expression. AI will be written as I exponents I under root plus I plus 1 under root I plus 1 all the way n under root n plus n plus 1 under root n plus 1. Okay? So this is the weird one that I need to construct. So here I can be equal to 2, 3, all the way n plus 1. All right, that's for AI. Then what about BI? BI is something quite similar, but just basically skip about 1 term. Still I plus 1 under root, I plus 1, all the way. Instead of having the last 2 terms, I'm just going to have only 1 term, under root n. You see? AI and BI, they're quite similar, right? So in this part, I'll let I equals to 2, 3, all the way to n. And I'll let Bn plus 1 equals to 0. Okay, this is all by my definition. And what about CI? CI is even more crazy. CI equals to AI to the power of I minus 1, AI to the power of I minus 2, BI, all the way AI, BI, I minus 2, BI, I minus 1. So this one looks like the binomial theorem, right? Quite look the binomial theorem. So I can be 2, 3, all the way, whatever, whatever. All right. Why I'm doing this? I'm doing this for a reason. Because I want to use my AI, BI, CI to denote whatever needs to be proved or whatever is given by the question. Right? So a quick observation you can find out. Actually, xn plus 1 equals to A2. xn equals to B2. Is that right? Let's have a quick observation. A2, okay, xn plus 1 basically means that I'm going to do this all the way to n plus 1. Look at the first line of my screen, okay? So this guy goes to what? And under root n plus is actually all the way to under root n plus under n plus 1 root n plus 1, right? So this guy will be exactly the same as A2, right? Because my AI starts from I can be 2, 3, 4, all the way to n plus 1. So xn plus 1 will be equal to n2, will be equal to A2. And what about B2? B2 is actually equals to xn, is it right? If we have xn, you're going to have 2 under root 2 plus under cube 3 all the way to under root n. So if we look at the BI expression, if I change I into 2, you're going to have exactly the same thing. I think this part is quite understandable, right? All right, so let's continue. Also, I can find out AI minus BI times CI. Let's have a look at it, how this part looks like. According to our definition, we're going to see this is our definition, right? So AI times CI can be equal with what? AI to to the power of AI. AI to the power of I minus 1 BI. All the way AI square. BI, I minus 2. AI, BI, I minus 1. Right? This is AI times CI. Then what about BI times CI? BI times CI should be AI, I minus 1 BI. AI, I minus 2, BI square. All the way AI, BI, I minus 1. BI to the power of I. Is that right? If I do a subtraction between the upper one and the lower one, check it out. This part will be cancelled. This part will be cancelled. All the way, this part will be cancelled. Only remaining the first one and the last one. Is that right? Equals to AI to the power of I minus BI to the power of I. So far, so good? Okay, moving forward, this AI to the power of I, what is AI? AI is here. To the power of I, you just basically eliminate this part, right? You only want to have, you crossed out all those I under root. You only have I plus 1 under root all the way. BI to the power of I, exactly the same thing. You're going to cross out all those, leaving everything remainder, right? So that one will be exactly equals to what? I'm just going to highlight it here. It's going to be this part minus this part, right? Well, this part minus this part is actually equals to what? AI plus 1 minus PI plus 1. Is that right? This is quite understandable, right? So this part is going to be AI plus 1. This term is going to be BI plus 1. All right? Just try to follow exactly the same fashion. All right. So I'm going to have AI minus BI times CI equals to what? AI plus 1 minus BI plus 1. So therefore, AI minus BI will be equal to, I'm just going to make I'm just going to divide CI on the two sides of the equation. AI plus 1 minus BI plus 1 over CI, right? I can be 2, 3, all the way to n. Okay, look at that. AI minus BI equals to AI plus 1 minus BI plus 1 over CI. What I'm going to do is I'm just going to print out everything one after another. I'm going to do what? So that one being said means what? It means, I'm just going to see, okay? It actually means if I multiple the n terms together, so this is going to be A1 minus B1 equals to A2 minus B2 divided by C1, right? A2 minus B2 will be equals to A3 minus B3 over C2. A3 minus B3 will be equal to A4 minus B4 C3, all the way AN plus 1 minus BN plus 1. Oh, I mean AN, excuse me. I don't have to go for AN plus 1. AN minus BN will be equal to AN plus 1 minus BN plus 1 divided by CN, right? So I'm going to stop here for a sec. I think I have a typo here. You don't have to write the first one because your BI is defined from I equals to 2. Still remember? So there's not the first one. All your expression starts from the second one. Okay, I have a typo here because your B expression starts with I equals to 2, and we define it Bn plus 1 equals to 0. Okay, this is my, this is like a typo I have here. What's gonna happen is I'm just gonna multiple all the left together and multiple all the right together. As long as you multiple them together, you see a lot of terms can be cancelled. You see? Everything can be cancelled. So put everything together, you'll be only have the last term. Is that right? So you're going to have what? You're going to have an plus 1 minus bn plus 1 will be equal to n plus 1 to the power of 1 over n plus 1 to the power of 1 over 1n plus 1. 1 over n plus 1. Okay? So far, so good? All right. So moving forward, what we can do is that we can find out actually A2 minus B2 according to our definition. Oops, that's the color. A2 minus B2 will be equal to an plus 1. I mean, here, let me just repeat it one more time. I'm just going to put everything together, right? I'm just going to put everything together, and most of the term can be canceled out, right? And at the same time, I find out an plus 1 minus bn plus 1. This part, an plus 1 minus bn plus 1. That one is not difficult part. I'm just going to put like, I'm just going to let, right, I equals to n plus 1. I'm going to let I equals n plus 1. So an plus 1 will be equal to n plus 1 to the power of 1 over n plus 1, right? This is going to be an plus 1. Then what about bn plus 1? Bn plus 1 is actually 0. It's defined by my definition. So this is exactly this one equals 0 will equal to n plus 1 to the power of 1 over n plus 1, right? So if we put everything together, we'll find out that A2 minus B2 will be exactly equals to an plus 1 minus bn plus 1, C2, C3, all the way to Cn. Is that right? This is actually, you cross out these two forms, you'll be able to get them together. And then moving forward, plug in the value. You're going to have what? A2 minus B2 will be equal to n plus 1, 1 over n plus 1, C2, C3, all the way to Cn. Is that right? Okay, look at here. AK, okay, let me see. A is actually such a, oops, sorry. A is actually such a nasty expression. This is for AI, right? BI is also a nasty expression. But of course, you can find out AI is actually greater than BI, right? And they should be all greater than I to the power of I. Is that right? You basically find out, you see, they have some more nasty things behind. So this guy will be greater than I to the power of I. So that being said, oops. So that being said, you'll have such an expression. AK is greater to BK, which is greater or equal to K under root K. And CK is actually what? The combination between AK and BK, right? You can actually find out, this is very easy to prove. CK will be greater or equal to K times K minus 1 to the power of K. All right? So that one being said will be greater than K times K minus 1, K plus 1. All right. So what I'm trying to do here, maybe we totally get lost. What I'm trying to do here, what I'm trying to do is here, I'm trying to prove xn plus 1 minus xn is lesser than 1 over n factorial. What is xn plus 1? Do you still remember? Xn plus 1 is A2. Xn is B2. So therefore, xn plus 1 minus xn will be equal to A2 minus B2. Right? Will be, yes, equal to A2 minus B2. And what is A2 minus B2? We just calculate it out. Okay? This guy will be equal to n plus 1 to the power of 1 over n plus 1, C2 all the way to Cn. Because CK, you have such a relationship. So I plug in this value from C2 all the way to Cn. So this expression will be lesser than 1 over n factorial, n plus 1, n plus to the power of 1 over n plus 1, n to the power of n minus 1, n plus 1, right? You just basically plug in the value and make sure this is only one ck. You're going to do that all the way to c factorial, from c2 all the way to cn. So that one will actually lesser than n 1 over n factorial. Okay, what is that? That's exactly what we need. We want to make sure xn plus 1 minus xn is lesser than 1 over n factorial. So these will be xn plus 1 minus xn lesser than 1 over n factorial. Okay, this is a crazy problem. And first of all, it takes forever for you to figure out how to have the AI, BI, CI construct in such a way. Second, even though you know, you have to figure out all those scaling to make sure what's the relationship between A2 minus B2. And then figure out another scaling about CK, so on and so forth. So totally, you do not really have to remember this problem, but what I'm trying to say is that sometimes whenever they want to give you a crazy problem, you need to do the construction. So the construction sometimes it really feels like it comes from nowhere, but you know what? It doesn't really come from nowhere. It comes from their experience. If you know this problem, in the future you see something similar, you might be able to come up with something similar as well. You know what? Go back, think about it, and you might feel the beauty of this problem. This construction is very crazy, but it actually converts the problem. You see, at the very beginning, the variable actually contains to n, right? Xn can be 1, 2, 3, 4, 4, 5. Well, after you do the construction, the n is no longer a variable, while the variable comes to I. So this is kind of like a conversion from one set of problem into another set of problem. All right? So that's pretty much the solution for this problem. I think this is a crazy problem, and as long as you understand, you know, we're trying to do this construction and convert the problem from the n to I, you kind of understand the focus point of this problem. All right? All right, I think that's pretty much for this solution. And I think this problem is super crazy, so we don't really have to spend too much effort. As long as you understand the big direction, it's good enough. All right, so let's continue our lecture. Any problems? So far, so good? I'll send you guys the video link, then you can go back to check it out line by line. Okay, so in the last lecture, like I mentioned, we focused how to use the construction to solve the algebra-related problem. In today's lecture, we're going to use the construction to pretty much focus the number theory related problems. So today's construction is construction in number theory. Okay, trust me, number theory actually use construction a lot, and sometimes a very smart construction can significantly save your time. Okay, and the number theory, if you can do a quick recall what we did for the number theory will actually contains two major parts. One is the normal number theory problems, you know, divisibility, you know, all those kind of things. The other one is actually what? The Diophantine equation, right? Diophantine equation and its integer solution is actually something very important for the number theory as well. So today's lecture, we're going to give you a bunch of problems basically for the regular number theory problems and the Diophantine equation problems. All right, so let's get started from the Diophantine equation problem first. I think these are considered to be relatively easy part. Okay, so our problem, let's have a look. Our first problem is a problem come from here. So this problem says, proof there are infinitely many positive integer solution pairs of the following equation. Like we mentioned previously, if you can recall, as long as you see infinitely many, most of the time, you'll be able to see this is the construction-related problem, right? As long as I ask you something does not exist, this is proof by contradiction. Something exists, you just find one, that's it. Something exists and infinitely many, what are you gonna do? Always go for the construction. Before we jump to the construction, let me give you a big direction. This is the big direction. What are you going to do? Big direction. If you are trying to find infinitely many pairs of solutions, the big direction always go for 2. either you find one pair of the solution, I don't know, A, B, C, I'll give you an example, and then you try to multiply them using a specific coefficient m. Okay, so normally speaking, m times A, m times B, m times C will also be a pair of solution, right? We're not talking for this problem, but generally speaking, when you have a set of solution, you put a big coefficient, most of the time, it still be a solution. And what you're going to do is you're going to do some magic for this coefficient. Let this coefficient equals to some weird terms. And when this coefficient is changing, so all the solution pairs is also changing as well. Is that right? If you can prove there are infinitely many of m coefficient, then you can prove there are infinitely many solution pairs. This is one big direction. The second big direction is exactly the same. As long as you find ABC is a pair of solutions, what you're going to do is instead of putting a big coefficient m, you're going to add an m to this, add an m to this, add an m to this. All right, as long as you can prove m plus A, m plus B, m plus C is also a solution. Plus, you can do some magic for m, make sure that m can be infinitely many. Then you're basically creating infinitely many solution pairs. Is that right? So this is actually something very important. You are trying to create an m and put the m as a seed. As long as the m is changing, you'll be able to find the new solution pairs will be changing. So this is something extremely important. Okay? So far, so good. I know this is an easy problem. Some of them already find it right away, but I want to use this easy problem to give you guys a big direction. What are you going to do for this type of problems? Okay, so for this, first of all, a quick observation, we find it's quite similar to Pythagorean theorem. X squared plus y squared equals to z squared. Is that right? So that being said, you will be able to find what? A squared plus b squared equals to c squared, right? You have a Pythagorean triple, and you make sure this equation holds. Next step, you want to use this seed to create more and more solution pairs, right? Like I said, most likely you have two big directions. Either multiple them using coefficients or adding them as another extra number. I think since you have a perfect square here, so I don't think adding them together might not be a good option, right? You're probably going to go for multiple them together, right? So who can tell me what you need to multiple in order to make sure? Probably you're going to multiple the m, right? ma squared plus mb squared equals to cmc squared. This is perfect, no problem. But you need to tell me what is the value for m, right? Again, like I said, this m cannot come from nowhere. It must come from ABC, right? It cannot be a massive, right? It cannot be from energy, but it must come from what? It must come from the value given by the question. Is that right? So who can tell me what this m should be? This m must be a relationship with ABC, right? If m is equal to 3, I'm sorry, this is totally wrong direction. M must be a number defined by using ABC. As long as ABC is changing, m is changing. So everyone is changing. So who can tell me what is the value for this m?
Oh, I actually did it differently.
Yeah, you can do it differently, but if you follow my direction, who can tell me what is the value for m? We want mc squared equals power of 6, so m equal to c squared. Yes, that's a perfect solution, eh? M can be equal to c squared, is it right?
Yes.
Perfect. What else? I can actually find a lot of m. I'm going to give you one m. M can be equal to c to the power of 3k plus 2. Is that right? That being said means what? A ck plus 2 square plus b c 3k plus 2 square equals to ck plus 1 to the power of 6. Is that right? So that being said, as long as you change, okay, this is like a Pythagorean theorem, right? Nothing really special. As long as you can give different values for k, then you will generate different AIMEs, right? As long as you generate different AIMEs, then you will be able to find there are infinitely many pairs of solutions fitting this Diophantine equation. Is that right? So try to understand the beat, okay? This problem, always the big direction. Try to construct a seed and then times them using M or adding them using M. Taking from there, you'll be able to get the right solution. Okay? And also, I know that if you go for M equals to C squared, it's even easier, right? But again, nevertheless, this M must be determined using ABC. It cannot be a number 3, 5, 6, right? Because ABC is changing, M is changing, and then they will create another pairs of ABC. Then this is going to be like a snowball effect, right? Like the domino effect. You can have more and more M's. All right, so if we're all good, let's go for another problem. Quite alike. But the second problem is a little bit, you need to think about it, how to create this M. Same thing. Proof, there are infinitely many positive integer solutions of the following equation. Same thing. You need to create something low-key, and then from something low-key, you get what you need. But this problem, I don't want to waste too much of time, okay? I can give you the solution right away because this is nothing but you just create something, find out what is the correct one, right? So this one, this is one possible solution. You can have infinitely many possible solutions. You can do something like this. 9k cubed minus 1 cube. 9k to the power of 4 minus 3k cube. 1 equals to 9k to the power of 4, 3. This is the challenging part is you have a 1 here, right? You won't be able to take it out by using 1. You need to find a 1 solution, a solution pair, x, y, z. And then taking from there, doing some tweak to make sure you can construct out such a form. I think this is more like you need to really know this, right? Really think about it. In today's assignment, I'm going to give you some other similar equations. You need to guess out how to construct the M, how to construct all the coefficients to make sure this identity holds.
Wait,
okay?
So you need to guess how to construct it?
For this part, you need to know something. You need to guess out something. Well, for the first problem, you can actually have a seed, right? Taken from the seed, you get what you need. Or the second problem, you guess more than you have the seed.
Okay.
Okay, let's go for the third problem. The third problem, one more time, you need to have a seed. And taking from the seed, you can get what you need. Okay, question number 3. Yeah, this is a problem from 2007 Chinese MO winter camp questions. For any positive integer n, please find out 2n plus 1 positive integers ai, 2n plus 1 is an odd number, such that they form an arithmetic sequence and their product is a perfect square number. You need to find out 2n plus 1 numbers. First of all, they must be an arithmetic sequence. Second, their product must be a perfect square numbers. Think about it. How are we going to do for this problem? You're basically having two conditions, right? One is arithmetic. And the other one is the product is a perfect square number. Most likely, I don't think you can get started altogether. You probably like to create an arithmetic sequence and then do some magic to make sure this arithmetic sequence can be like all the term of this arithmetic sequence can go to a perfect square number. Or you can get started with a bunch of numbers, make their product can be a perfect square number, and then do some other tweak to make sure those guys can create an arithmetic sequence. Is that right? So you're kind of enhancing or enriching your condition. You won't be able to jump to the direct solution right away, right? Think about it. Who has some ideas to this problem? Now, in this lecture, I really want you guys to get involved, right? More and more important is you think about, you need to train your thoughts. Whenever you see a problem, what's the breaking point? Like I said, two conditions. You must meet one condition. You must construct out a sequence that meet first condition, and then try to enrich your condition, right? And then make this sequence also meet the second condition, and voila, you get what you need. And this is the big direction when you solve a problem.
Factorial.
Condition 1, arithmetic sequence. Condition 2, perfect square number. So all those construction problems are like this. They're so smart. If you know it, it's going to take you maybe a couple of lines. If you don't know it, it's going to take you a couple of weeks, right? Just like, how can you find? But there's a reasoning, right? There's not like we just jump from nowhere. So my suggestion is, why don't you find something meets like one condition, and then you can go for the other condition by doing some enrichment. So this is where construction kicks in, right? So let me give you some hint, maybe. If I want you to create a sequence, their multiple is a perfect square number. Okay? If I wanted to create a sequence and their multiple is a perfect square number, is there anything you want to think about it? Is there anything looks a little bit magic?
Sum of consecutive odd numbers is equal to the nth squared.
Is that right? Is that right? Something, this is kind of like a big direction that Joey mentioned, right? Some consecutive numbers might be able to create it out. What else? When you do the construction, it should come from something very brief, very easy, right? So I won't ask you from like 265, 266, right? It doesn't make sense. And there must be from something very basic. So think about it. Let's think about this problem altogether, right? When you have this problem, you're totally blind. You have nothing to get started with. Let's say your goal is trying to create a construction. Let's say this is your first condition, you want to meet it first, and this is the second condition, you want to meet it second. First condition, you want to have a sequence. All the terms, put them together, it creates a what? A perfect square number. So let me see something like this. A1, A2, all the way to AN. If their multiple equals to n, this is not even perfect square number, right? I just want to say I have a random sequence, but I want to make sure their multiple together equals to n. However, this is no guarantee n can be a perfect square number, right? Like I said previously, what are you going to do? You're going to do some magic. Multiple every single term by using something, or add every single term by using something, right? That being said, you'll be able to enrich your sequence and get a more flowery sequence. Is that right? If this is our seed, basic one, what I'm going to do is I'm going to do something like this. N minus a times A1, N times A2, N times A3, all the way N times a 2n plus 1, right? Because I'm talking about 2n plus 1, right? So that being said, this is going to be what? N to the power of 2n plus 2. Is that right? Because we have 2n plus 1 a's on the left-hand side. I'm going to give an n for every single number. So in total, you'll have something like this. Oh my God, this is going to be a perfect square number. Is that right? So that being said, as long as you have 2n plus 1 numbers, every single number, you want to plug a k here. You want to plug in an n here, then you will be able to construct, you see, n, then you will be able to construct a perfect square number, right? We kind of already have what we need. And then moving forward, I need to enrich one more step. I want to have all those n here, but I want to have a arithmetic sequence. I can't have a random sequence, arithmetic sequence. So what am I going to do? I'm just going to do something as easy as possible. I'm going to let AI equals to I times n. Is that right? I times n, this is going to be arithmetic sequence, and also a1 times a2 all the way to a2n plus 1 will be equals to 2n plus 1, 2n plus 1 factorial k to the power of 2n plus 1. Is that right? N to the power of, I'm going to use this, n to the power of 2n plus 1. Is that right? So far, so good?
Yeah.
But I want to make sure, I want to further enrich. This is, okay, this is correct, but this is no guarantee to be a perfect square number. What I'm going to do, keep enriching my condition. I'm going to put some magic for this n, right? As long as I can let n equals to 2n plus 1 factorial, I will be able to say this is going to be a perfect square number. Is it right? 2n plus 1 factorial, because this is going to be what? 2n plus 1 to the power factorial to the power of 2n plus 2. 2n plus 2. This is going to be a perfect square number. So try to understand this, okay? This is like the magic. This is like the magic how to solve this problem. But this is magic really you can learn this magic, right? We always get started with something low key. I want to create like a sequence. Their product is a perfect square number. Okay, so that one is easy. As long as I create something, that's going to be okay. And then I need to enrich my condition. How to enrich my condition? I'm going to try to give specific values, specific ingredients to this already created sequence. I'm going to make I times n. So that's going to be arithmetic, right? Arithmetic plus all of this, I have something like this. But this is not guaranteed to be a perfect square number. Then what am I going to do? I'm just going to let n equals to a specific number. That will help us solve this problem. Try to understand the beauty of this problem. So like I said, we always get started with a seed, and then taking from there, gradually make it more and more complicated to enrich the condition, and you will get what you need. We're going to use this strategy one more time in a latter problem, a more complicated problem. Okay, hope you guys just bear in mind, this is a common strategy to solve problems. Okay, so far so good? Okay. Oh, good. Let's go for another difficult problem. This is not super difficult. It's kind of okay. And we like to show you guys how to solve all those similar problems like this. Okay. This problem is actually a very common problem. In any kind of math competitions, they randomly ask you this type of problem. Prove there exist 5 integers. Their product does not equal to 0, means none of them equal to 0. If you subtract 1 from each of the number, the remaining numbers will still keep the same. So that being said, you have something like this, right? You have what? A, B, C, D, E, 5 numbers. you want to make sure A, B, C, D, E, the product equals to, if you minus 1 for each of them, the remaining part will still be the same, right? The product of these 5 numbers is the same as everyone minus 1. You put them together. I think to go here, you don't need any kind of inspiration or magic, right? You can come here. Okay, so basically you're trying to solve an, what is called, you're trying to solve an Diophantine equation, right? So you're trying to find 5 integers, and to solve this Diophantine equation. Okay, if you really wanted to solve this equation, this is going to be a little bit challenging because this is like a 5 variable and to the power of 6. 1, 2, 3, 4. Yeah, 5 different. Oh, excuse me. So 5 different variable to the power of 5 equations. This is very difficult for us to solve, right? But the good part is the question doesn't really ask you to give a completely solve. They just want you to give like one pair of solutions good enough. Is that right? Because it says proof there exist 5 numbers. And as long as you can use your magic, create these 5 numbers, you're good to go. Well, the difficult part is that there are 5 variables to the power of 5. How can we get started? Any ideas? 5 variable to the power of 5. I don't think you can solve it in a regular way, right? Yeah. Okay. We see somebody already finding. Okay. We see somebody already finding out. Okay. That is good. You see, you solve this problem. Maybe we have to move on to the other problem. Okay. Hey, James, can you tell me how do you think about it?
Okay. So you basically notice that if you have like two numbers like -5 and 6, right, and then you subtract 1 to each of them, then you have -6 and 5, right? So you can make these pairs that that don't really like, instead of like -5 and 6 here, I could put it to like -1 million and then 1 million and 1, right? It's still the same. So if you have like some pair like this, then they're, the next like product is, if you subtract them by 1, is the same. So what you can do is if we had like an even number, like prove there exists 6 integers, then we can just put a bunch of these pairs, right? But because we have 5 integers, we need to find something like this, except it has like an odd number of numbers. So what I did was I first just put one of these pairs down, right? -5 and 6, and then I tried to do the problem for 3, and then I realized that -1, 3, and 4 works. So yeah,
Okay.
just some guess and check for those 3.
Okay. If I change this problem to prove there exists infinitely many positive integers for this solution, can you do the same thing?
Oh, wait, I'm gonna have to think about that.
Yeah, I think your solution is correct. Yes, your solution is correct. You can do some guess and now, right? You can do some guess and taking from there you get what you need. Okay, that's perfect. My solution is more like the academic solution. I'm trying to teach you what is the big direction to solve all those problems. You can actually prove there are infinity many, not only 5 numbers, there are 5 million numbers, good enough, 5 million pairs, so on and so forth. Well, to solve this problem, you have a very, what should I say, patternized solution.
Wait, okay. Here, I got it. So if you have, so basically we have the even number pair, right?
Mhm.
So then we just need a pair of 3. And a pair of 3, we can actually generate infinite number of those. If we have like 2 positive numbers and a negative number, and the positive numbers are next to each other, like instead of -1, 3, and 4, we could have 5 and 6, right? And then if we subtract 1 from both of those, we get 4 and 5. Basically, we're going from a 6 to a 4, basically. So we can, on the negative side, we can go from a 4 to a 6, but that would jump by 2. So we can have instead like a 2 to a 3. So basically you can have -2, 5, and 6, right?
Okay, you see?
And then, or you could have -3, 7, and 8 or something.
Okay, you see, I just want to give some hard time to James. Looks like I can't. You know what? Let me change this problem to this. A1. Okay. So James, you can tell me if you can do this by using guess out. A1, A2, A 2019 equals to A1 minus 1, A2 minus 2, A 2019 minus 2019. Again, you have infinitely many solutions for this. Can you give it right away?
No. Wait.
No worries, no worries. So I think James' solution is very smart because he did some search, he did some trials, all right, and then find it. But I think I'm going to give you something more generalized solution, right? A patternized solution. Even though you do a weird thing like this, I can solve it in about 15 minutes. Okay, how to do this? Big direction. Direction is always important, right? This is our guideline. You do nothing but two things. Reduce your variables. Reduce your orders. Reduce your variables. That's 2019 different variables, right? Reduce orders. They're like 2019 orders. You want to reduce them. Of course, when you reduce them, you're going to have to sacrifice a little bit, right? You can't just reduce them randomly. You need to do a little bit of compromise. So what I'm going to do is you can do something like that. You can do something like this. You don't like B, C, D, E, F, like so many things, right? I'm just going to do this. Let B equals to A minus 1. B equals to A minus 1. Let C equals to B minus 1. Let D equals to C minus 1. Somebody will say, hey, Alex, you're going to be crazy. It is not possible. It is not guaranteed that B equals to A minus 1. It is not guaranteed that C equals to B. Yeah, you're all good. But I can guarantee to tell you, I will be able to find a solution for this because there are infinitely many solutions. You don't really care which solution that I find out, right? As long as I'm doing this, think about it. What is going to happen here? The left-hand side is going to go to what? A minus 1, A minus 2, A minus 3, E. Right-hand side will be A minus 1, A minus 2, A minus 3, A minus 4, E minus 1. Is that right? So that being said, see, a lot of terms can be cancelled. You directly jump to A times E equals to A minus 4, E minus 1. Right? 4E plus A equals to 4. This is a Diophantine equation for sure, but these Diophantine equations have infinitely many solutions, right? You don't have to think too much. You can just close your eyes, give you any kind of solution. Let's say A equals to 8, E equals to minus 1. As long as you have this, what are you going to do? You can just basically plug it back, and you'll have the B, C, D. Is that right? So these actually give you a strategy. Even though you see more stuff, you see this like 2019 stuff. You don't have to care about it. You just keep replacing A2. I don't know if you follow me. A2 equals to what? A1 minus 1, right? A1 minus 1. B2, A3 equals what? A2 minus 1. As long as you're doing this, you will be able to cancel out most of the terms. Is that right? At the end of the day, you're still looking at a very brief term, something like this. A1 times, I don't know, A 2019 equals to maybe A1 minus 2018, right? And A 2019 minus 1. You will still be able to figure out A1 and A 2019. As long as you have them, plug it back. You'll be able to have so many values. So it doesn't matter, it gives you what kind of weird forms, right? Using my solution, using my academic solution, you will be able to solve out all those kind of situations. So far, so good? So this is actually a very important, okay, this is not a super difficult problem, but try to understand the pattern. You should have the courage to do such a great simplification. When you have this simplification, most of the problem will be solved fairly quick. So far, so good? Yeah, I think James actually make it quite similar. Yeah, just basically you minus 1, and you get what you need. If all good, let's go to a relatively difficult problem. I think this is question number 14 if we continue our previous lecture's problem. This one, we'll need some more time to think about it. Proof: there are infinitely many positive integer solution pairs of the following equation. Again, like I said, as long as you see the infinitely many, most likely you're going to use the construction method, right? Construction. And again, I think the strategies are exactly the same. Your goal is trying to, the big direction is either reduce the number of variables, or you need to reduce the order of your equation, right? But this time, I don't think you just directly equals to x minus 1 or something, x equals to y minus 1. I don't think this is going to help. You're going to do something a little bit more flowery to make it happen. How to reduce the variable, how to reduce the order of the problem. Observation. How is it possible? They don't have to be positive. They can be negative. They can be negative, right? Why it is not possible? Says possible. Oh yeah. So okay, maybe that's my bad. Not possible. Yeah. Infinite many integers. I think there's a yeah. So it couldn't be possible, right? If it is all positive integers, right? Then this is not going to happen, right? They can be negative. Yeah, it should be negative, right? You should have the negative in kicks in. Otherwise, it won't really hold. Yeah, I think this is my typo. Because most of them, they're actually written in like Chinese or something. I have to translate them into most of those countries are actually Eastern European countries. They don't have the English version. What I read is like a Chinese book. This is written in Chinese, and then I'm going to retranslate into English. And most of the Russian problems as well. So, okay. Yeah, that's a good catch. Yeah, there's not positive. It is impossible to be positive. It can be. Yeah, I have like a bunch of Chinese books, like international IMO collections, or like the shortcut to IMO. You know, all those kind of things. They give you a lot of analysis, how to basically do the problems altogether, right? A problem like this, what is the big direction? I think this is actually something very interesting I'd like to show you guys. You see, you have the 3 square terms on the left, 3 cubic terms on the right. This is very nasty, right? Because you have so many variables and so many high order things, you won't be able to make it happen. I need to reduce my number of variables. I need to reduce my order. So some students said, why don't I let x equals to 0? I'll say, whoa. Okay, x equals 0, that's going to really significantly reduce your problem, right? Reduce the complexity of the problem. But you're having a huge sacrifice. There are actually 3 variables, 3 moving parts. Now you're only going to make them 2 moving parts, right? X is equals to 0. This is actually a gigantic sacrifice. So I don't think x equals to 0 is a good solution. You want to do something similar like we did before. Find out the relationship between x and y and a and b, and you still do not oversimplify this problem. So, any ideas? How can I think one of the things I hate a lot is there are 3 cubic terms. How can I reduce the 3 cubic terms? How can I reduce the 3 cubic terms? Maybe to 1. I don't think I can reduce them all, right? So I don't think they can go to 0, but at least do some magic to reduce them significantly. Who can just give me a big hypothesis? How can I manipulate x, y, z I can make sure these 3 cubics can go to maybe even 1 cubic. Let them equal one another, right? Like Alan mentioned, let them equal to one another. This is a very big step, right? Let x equals to minus y. I know this is a huge step as well, right? But as long as you do this, what are you going to have? 2x squared z squared equals to z cubed. Is that right? You are not doing a huge sacrifice because still you're going to have like 3 variables. If you let x equals to 0, oh my God, there's only 1 variable, right? But if you have x equals to minus y, you're still having 2 variables. You're still having 3 variables. But it's going to significantly reduce the complexity of the problem. Is that right? I think as long as you see this, you're almost done for this problem. Why? So that being said, 2x squared equals to z squared, z minus 1. Is that right? So x squared equals to what? 2z squared, z minus 1. I think I'm already able to solve this problem. Who can tell me? Is there any kind of conditions for x and y, and I can successfully find a value for x? Bear in mind, there's not only one x. You're not here to solve the equation. You are trying to prove there are infinitely many pairs of the solution. I'm already writing it here. Who can tell me? Just one step away, you get a correct answer. Like I said, this is impossible for you to find an x value, 2, 3, 4, 5. Instead, you want to give me a set of x values, a series of x values which can meet the condition, or a series of kind of blah, blah, blah conditions. I can make sure this condition holds and my work is done. Yep. See James and Alan, they have the correct answer at the same time. In order to make sure this condition, my condition is asking what? This guy must have integer solution, right? In order to have integer solution, x must be an integer. X is what? A perfect square number equals to z squared. Okay, not a big deal. But this guy, as long as I can make sure, as long as this guy equals to a perfect square number, let's say k squared. So that being said, z equals to 2k squared plus 1, I will be able to determine the value for x, which is, right? And y, 2k cubed plus k. For sure, x, I need to take the negative one, right? If everything is positive, there's impossible, right? I need to take the negative one. To make sure there are some positive, some negative, make sure this original equation holds. So this problem, the beauty is exactly the same. What are you going to do? You're not doing any magic. You're not doing any magic. What you're going to do is try to be brief, try to be bold. Have one step for x. As long as you give x a specific value, then you will be able to solve x. See? This is actually something, the million-dollar question part. As long as you see the Diophantine equations do not go for a 1 equals to 0, that's a huge sacrifice. On the contrary, what you're going to do is try to find out some relationship. All those problems, if you see this in the future, you're going to see that all the correct solution is not have one value equals to 0, the other value equals to 1. So that's the reason why I didn't really suggest James' solution at the very beginning, because he gave me a value right away. I'm not saying his solution is incorrect, it's perfect, but instead of you give me a value 1, 2, 3, 4, no. I want you guys to give me something like this. So they are correlation. There's a correlationship into x, y, z. As long as one thing is changed, the other two things will change at the same time. This is exactly what I need. The same thing applies for the previous problem, right? As long as you give me a E, I'll be able to define an A. I'll be able to define a B, C, D. So this is the way how we solve all those problems. So far, so good? Okay, so far, so good? If all good, let's go for another difficult problem. I think this is 14, 15. I never remember the numbers, but you can check it out from the notes. So this is going to be, okay, the solution. Oh, no, not this guy. Okay, give me a sec. Because sometimes they don't really give you the good overview what is the entire picture looks like. They only give you a quick 1, 2, 3 positive integers. That's not what I need. This guy? Not this guy. I should have the double number thing. Just give me 1 sec. Sorry about that. I have it here. Yes, it's the hungry. It's a hungry problem. 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5, 6. This is positive integer short list. I hate this. 1, 2, 3, 4, 5, 6. This is not equal. If I really can't find them, I'll just write it for you. Okay. Okay, I'll just write it for you. This is not a long question, but I'll just write it for you. So this is a problem from 2014 IMO Hungry short list question. So this question goes like this. So I define a number I called a double number. A double number is defined in such a way that 2 instances of the same decimal form of any positive integers are put side by side. This is more like awful. So I give an example. 1, 2, 3. 1, 2, 3. 1, 2, 3 is like a decimal form of any kind of like a positive integer, right? It's okay. I'm going to put it twice. Another example, 306. 306. I put it twice side by side. Okay, this is I call it like a double number. For instance, 36036. This is not a double number because you're missing a 0, right? You're missing a 0. I think like the definition is very understandable. Just like any kind of positive integers, 4132, 4131. So put them twice side by side. These are considered to be a double number. Okay, with all of this, please prove there are infinitely many double numbers that are perfect square number. You see, these problems really look like the IMO problems, right? These are all says the same thing. They give you a definition, a weird definition, but this is not so weird, right? A double number, just write it twice, whatever. Proof, there are infinitely many double numbers that are perfect square number. There are infinitely many double numbers that are actually perfect square number. A problem like this, how do we get started? How do we get started? 1001, this is not a double number because like I said, it's like the same 1001, this is not a double number. This is like a palindrome number, right? It's the same from left to right and right to left. Double number means the same instances of the decimal form. You're going to write it twice. 1010.
Wait, maybe you can try finding multiples because you know all double numbers have to be like divisible by like something like 10001. So maybe you're trying to find multiples, like how to factor 100001.
Okay, I think that's where Stephen comes from. Yes. Okay, so Stephen means that's the multiple of 1001. Okay, that's a very good approach. So before we jump to there, let me ask you one question. The question give you all those double numbers, right? It basically give you 2 examples of the double numbers. If we want to do some magic, prove this double number is a perfect square number, so on and so forth, first thing first, I need to find a proper way to denote this double number. That is correct? I need to find a more mathematical way to denote this double number. Who can tell me? By using this example, maybe another example, 110, 110, who can tell me what is the mathematical way to denote a double number?
You can be like a multiplied by 10 to the power of n plus a.
A
Multiplied.
10 to the power of n plus 1, right?
Yeah.
Okay, that's a very good. So you guys all on the same page? This is like a double number. At least it looks like this, right? Okay, I'm just going to change it a little bit. Maybe 10 to the power of n. Let me change the color. 10 to the power of n plus 1. Let's say I'm going to put m. Okay, m and are all like coordinated. Okay. I don't think there's not too much I can say for this. And this is basically whatever power, right? For 10 to the power of n. That's it. Who can tell me for this m? Is there any specific constraints for the m? Or if there's anything you can put for m?
M can't be a square number.
A
Because
square
no
number.
matter what n is, 10 to the n plus 1 isn't a square number.
Oh yeah, that's yeah. So Andy, you're talking about how to prove this is a perfect square number, right? That is fantastic. But let's step back one more. Let's step back one more step, okay? Whenever I write this, for any kind of double numbers, I'm not talking about a perfect square number or just like not perfect square number, so on and so forth. All the double numbers can be written in such a form. And who can tell me, is there any constraint for m? M can be whatever it likes to be.
Oh yeah, the number of digits of m. Yeah.
Right, exactly. The number of digits of m must have some constraint. M can't be too big, neither too small. Is that right? If m is only 1 digit, but this is like 300 digits, this is not going to be a double number. Is that right? If m is too big, this is only 2 digits. This is like 1,000 digits. This is going to be a double number. This is not going to be a double number neither. Is that right? There's kind of a constraint for m. M's digit can't be too big, can't be too small. Actually, m must be here. Do you guys agree with me? M must be a n-digit number. Is that right? You guys follow me? M must be an n-digit number. I'll give an example, okay? Give me an example. 1, 1, 1, 1 will be written to what? Times 11, right? So this is to the power of 2. This is actually a 2-digit number. 1, 2, 3, 1, 2, 3. I can write this times 1, 2, 3, right? So this is going to be a 3-digit number. Is that right? The digits of m must be the same as the 10th power. Otherwise, you won't be able to make, because m cannot be too big, cannot be too small. You just want to make sure 1, 2, 3, 1, 2, 3, just exactly they're matching each other. Is there any magic for there? All good? Okay. If all good, so our goal is we need to prove 10 to the power of n plus 1 times m. This is going to be a perfect square number, right? This is a perfect square number. Okay. Perfect square number. Okay. 2 numbers. Their multiple is a perfect square number. I think your first reaction is a perfect square number means what? There must contain like a perfect square factor, right? Perfect square factor. Perfect square factor, right? as long as you have perfect square factor, you might be able to basically do some magic to see the perfect square number. I think this is very intuitive. Okay, this expression only has two terms. One is 10 to the power of n plus 1. This is something we are kind of okay. This is okay. The other one is m. M is totally like whatever number, right? Okay, to make sure we want to do some analysis, let's have some quick discussion for this. Because the perfect square number must have the perfect square factors. These perfect square factors might come from here, might come from here, or might be shared between here and here, right? These are only the three possible possibilities. It won't have anything else. So let's have a look at the first scenario. If 10 to the power of n plus 1 does not have square factors. It just have a square factor or does not have a square factor. Whenever I say square to the power of 2, 4, 6, they're all considered to be square, right? Just like even number of factors. Okay? You guys follow me? Yes or no?
Yeah.
First one. If this one does not have square factors, what does it mean? If you have no idea what it is, try to do some enumeration. 1, 2, 3, 4, 5, you get some idea what it is. If n equals to 1, you're looking at 11 times m, right? If you want to make sure, m is what? M is actually a one-digit number, right? Is it going to be a perfect square number? Forget about this. It's going to be impossible, right? What about n equals to 2? You're looking at 101 times m. But m needs to be a two-digit number. Think about it. 101 is what? It's a prime number. In order to make sure this guy is a perfect square number, m must contain 101's factor. Is that right? 101 is not a two-digit number. N equals to 3. N equals to 3 is 1001 times m. M must be a three-digit number, right? 1001, this is not a prime number. You do a factorization, 7 times 11 times 13. So that being said means what? 7, 11, 13, unfortunately, none of them are composite. They're all prime numbers. To make sure the entire expression becomes a positive, becomes a perfect square number, m at least, you need to have the 7, 11, 13 factor, right? You can have more, I don't really care, but at least you need to have these three factors. You want to create a perfect square number, right? But as long as you have these three factors, you're no longer looking at the three digits. Is that right? Same thing. N equals to 4. 10001 times m. M is a four-digit number, right? This guy is actually equal to 73 times 137. Again, you're looking at two prime numbers. Then m must at least have 73 and 137, these two factors. Is that right? Okay, up to here, you can save our time. This is going to be impossible. You keep writing, everything you're going to have here is going to be the prime numbers multiple. And m must have all those multiples. So m cannot be those four-digit or three-digit, so on and so forth. At least m must contain all the factors of the first expression. Is that right? You guys follow me? So that being said, so this scenario, impossible. If n 10 to the power of n plus 1 does not have any square factors, this is going to be impossible. Forget about it. So let's go for the second part. If 10 to the power of n does have a square factor, what is going to happen? Right? If it does have a square factor, what is going to happen? Again, people will say, how can I do this? You don't have to do this too much. What you're going to do is that you're going to do some enumeration. Think about it. If you have no idea, always started from enumeration. All the magic will speak for itself during the enumeration. These guys have square factors. Is it possible it has 2 square factors? Let's say from here. Is it possible you're going to have like 2 factors? Not to say square. Let's have a look at it too. This is impossible, right? These guys cannot be a multiple of 2, right? Is it going to be a multiple of 3? Who can tell me? Why? Why? A quick observation, 10 to the power of n cannot be a multiple of 3. Yeah, I think Alan has the correct direction. These days, we're no longer use, after we learn the modular arithmetic, right? We're no longer use 3k plus 1, you know, this kind of low techie thing. 10 is congruent to 1, modulo 3. 10n is congruent to 1 modulo 3. 10n plus 1 is congruent to 2 modulo 3. So this is impossible. This guy will never be a factor of 3. You should just keep writing, right? Is it going to be a factor of 4? You're going to be kidding me, right? This is going to be an odd number. 10 to the power of n plus 1 is an odd number, right? So it won't be a possible factor of 4. Is it going to be a factor of 5? It's going to be daydreaming, right? Because factor of 5, a multiple of 5 must be, the last digit will be always 0 or 5, right? 10 to the power of 1, the last digit is always 1. 6, you don't have to waste your time, right? 6 is actually the same as 4. They are composite numbers. You don't have to waste your time. Well, here's the interesting. Is it going to be a, I mean, this is all like square, right? This is all like square, not like 1, right? 1 square, 2 square, square, right? Is it going to be 7? Is 7 going to be a factor of 10 to the n plus 1? Is it 7 going to be a 7? I think this is quite possible, right? Even though I don't know what it is, but it looks like this is not something so magic, right? It is possible. Even though I have no idea what it is, but it is possible. Okay, let's say it is possible. Our work is not done. We need to find out the AIME, right? We only know the first part. We need to know the second part. Because our goal is saying that 10 to the power of n plus 1 times m. I want this guy to be a perfect square number, right? This is going to be a perfect square number. And if, for some reason, I can make sure this is a square of 7, this is going to be a multiple of 7 square, then what I have to do, I just let m equals to 10 to the power of n plus 1 divided by 7 square. I get what I need. Is that right? I just let m equals to 10 to the power of n plus 1. So therefore, these two guys add them together will be a multiple of 7 square. And my work is done. Is that right? But unfortunately, this is not correct as well. Why? I think all the way come to here, we think we're in a good track. Exactly. Just like Alan mentioned, m does not have enough digits. Because, like I said, m must be from here. This must be an n-digit number, right? If it goes like over 7 square, this is not going to be like an n-digit number. It's going to be maybe n minus 1 digit, right? You're divide 50. Divide 50, you're actually divide a lot. So it looks like I'm going to be stuck from here because I have no idea what am I going to do. Because this part, okay, 10 to the power of n plus 1, it is possible to be a multiple of 7 square, but I'm stuck. I have no idea how this m is. So here's the beauty of the construction method. Can I do something small, quick and dirty to make sure I'm eligible? You guys follow Alan? That's exactly the correct answer. Times 6 square. You times a 6 square, you're kind of like, right? At the very beginning, you divide 49. Now, and then you times another 36. Kind of you squeeze it back. So that being said, that is the correct solution for M. You know, this is like a construction method. Construction method in Chinese, we call it like 无字天书. You guys understand this? 无字天书. It's kind of like what should I say? It's kind of like a prophet. You know, prophet in the ancient Greek. Before you always go to like the war, you always go to the temple and ask, okay, are we gonna win the war or not? Unfortunately, the prophet will never tell you you're gonna win or you're not gonna win. The prophet will always say, flower rollings in the blood. You know, are we gonna win? Flower rollings in the blood. Or darkness all over the sky. So you know what? This is like a prophet myth, right? They never answer a question directly, but you always give you something very indirect. Construction method is something like this. You're all good to hear. This is more like a human being thinking, right? But you always need to jump a little bit to have the construction. Times 6 square. You will make sure m will be a n-digit number. So that's exactly what m should be. Is that right? As long as n to the power 10 to the power of n plus 1 is a multiple of 7 square, you can always construct such an m. Well, there's another thing we didn't figure out. How can we prove there are infinitely many n's such that 7 to the power of 2 is a multiple or it's a factor of 10 to the power of n plus 1? This part I think is easy. At your level, you shouldn't have a big problem figuring it out. I'm just going to give you this right away. Because according to the Euler's formula, right? Euler's torsion formula, this one is this. Is it right? Any objections to here? This is phi 49. Euler's torsion formula, right? Is that right? Euler's torsion formula, 10 to the power of phi 49 is congruent to 1 modulo 49. So actually, it's fairly easy for you to figure out this. 10 to the power of 21 is congruent to minus 1 modulo 49. This is like a basic calculation you figure out by yourself. So therefore, as long as you take n equals to 21 plus 41k plus 42k, you will always make sure 72 is a divisor of 10 to the power of n plus 1. So far, so good? Yeah, you can put 7 or something. Yeah, you just pick up 1. It's okay. But 1 is not enough, right? You need to put infinitely, right? 1 is not good enough. You need to put like infinity n's, not only 1 n's. There are infinite many n's. So far, so good? Understand the beauty of the construction. The last problem I'll be showing you and actually reveals even more beauty of the construction. It handles like a dream. When you wake up, right, you have the right answer right in front of me. But when do you wake up? That's actually that's the $1 million question. So far, so good? Any questions? Good? Yeah, I just want to have some feedback from all the guys, right? We're all here, right? Like for this lecture, you don't have to understand every single step. You understand big direction is good enough. a big direction. And then for the really tiny things, you go back to you can watch my video like 1 time, 3 times, whatever. You can understand the details. But the big direction, how do we think, is the $1 million question. Okay, let's go for the last problem for today's lecture. I love the last problem as well. These are all the beautiful problems. This is a Chinese AIME winter cap problem. This is 2012 Chinese AIME winter cap question. Proof: there exist 2016 different positive integers, a1 all the way to a2016, such that for any given I is lesser than j is lesser than 2016, you can make sure ai minus aj, the difference absolute value, is the same as the greatest common divisor of ai. The greatest common divisor, ai and aj. The greatest common divisor of ai and aj. Actually, trust me, this problem you should find something inharmonic right away. This is a 2012 problem. How come they ask you to prove 2016? That one doesn't make sense. It should go for 2012, right? According to something like our common practice, right? So bear in mind, this is one thing you need to think about later. Later, I'll review why it's 2016. Because 2016, it doesn't matter. Yeah, you're 4 years ahead, right? You're foreseeing the future, seeing into the future. Later, you're going to find out 2016, it doesn't matter. You can be whatever numbers. Okay. A problem like this, how do we get started? That's a crazy, that's a $1 million question you want to ask for yourself, right? This is not a crazy problem, but that's actually a very interesting problem. But this is a $1 million question you ask for yourself. How to prove I, j, blah, 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 ai minus aj is the greatest common divisor of a and g. Again, like we keep saying from day one, if we want to do something very intuitive, n equals to 1, right? It for sure, a1's absolute is a1 itself. N equals to 2. I think it's kind of easy for you to find the two numbers. Their absolute value is their greatest common divisor, right? Their difference absolute value is greatest common divisor, right? Who can give me an example for this? Reach two numbers, their greatest common divisor is actually the difference of these two numbers. Okay. Alan has one. Do we have some numbers even more constellations? Alan's number, you need to think about it. A 2, 1, 2, and plus 1, yes. Just I plus 1, that's it, right? Because I and I plus 1, they must coprime, right? Any consecutive two numbers must coprime, and their difference must be equal to 1. N equals to 3. I think this is going to be a little bit difficult, because this is not only for two numbers. This must be any number, any ai minus aj must be the absolute value equals to ai, aj's greatest common divisor, right? Then what about n equals to 4? You know, like this complexity is the complexity is increasing exponentially, right? So like the first couple of numbers, you can maybe count your fingers, you can figure it out. As long as you go to 4 or go to 5, it's going to be increasing like crazy. Okay. A problem like this, what are we going to do? A problem like this, what are we going to do? This is actually, we're going to use the inductive construction. Do you still remember in the first lecture we said the construction method actually contains two. One is the direct construction. Everything we saw that before is the direct construction. I construct something and then I solve it out. Well, there's another type of construction. We call it the inductive construction. I told you previously that's not a focus for our lecture for now, because we're going to cover this in the induction method. This is the construction method. Let's focus on the construction. Well, induction method, we're going to spend more time talking about the inductive construction. But today, I'd like to give you guys a little bit idea how this inductive construction works. Our direct construction is I just construct something out, and that's it. Voila, my work is done, right? Well, the inductive construction goes like this. Pretty much like the mathematical induction method. I assume every one of you guys should be familiar. Whenever n equals to k, you want to make it hold. The property holds, right? You want to prove n equals to k plus 1. The property holds, right? The inductive construction method are quite similar. You want to construct something works for k, n equals to k. This is what you constructed. From here, you want to use your as constructed result to construct out k plus 1. Same thing. As long as you have n minus k works, you want to prove n minus k plus 1 works. As long as you are doing something like, somebody already has an answer? I don't know. I didn't really check it. My solution is way more complicated than that. Yeah, if you have a better solution, then I have to stop. I have to stop. So the other guys, please help me verify James' solution. It is correct or not. I don't know. Because my solution is way more complicated. So this is the construction method. Okay, this is the inductive construction. So how to make an inductive construction? This part we have to go back to what we talked about before. All those kind of construction things, the sequence construction things whatsoever, either, let's say A1, A2, all the way to AN, right? If this one is okay, either you want to times K, right? Or you want to plus K. Is that right? Still remember? This is what we mentioned at the very beginning. These are the two major ways how do you do the construction. Okay, if that's the case, let's have a quick look. Let's get started with this. Multiple K. AI minus AJ multiple AI AJ, right? AI minus AJ absolute equals to the greatest common divisor of AI and AJ. If I multiple by K, it is okay. This is going to be K numbers. And this is also like the greatest common divisor will increase by K. Oh, good. Okay, oh, good. I think this is quite understandable. However, I'm still working on K numbers, right? Times a K, there's no way for me to add a number. There's still K numbers. I do all the flowery things, all the magic still works for K numbers. I don't really get what I need. Is that right? So maybe doing this is not what we need. So let's have a look at for the second part. Add a number. Add a number A1 all the way to AJ, right? AN, excuse me, not AJ, AN. You want to go to M plus A1, M plus A2, M plus AN, right? Okay. AI minus AJ, absolute. AI AJ, greatest common divisor, right? All right. This part, AI minus AJ, if I output an M, if I output an AM, okay, AI put an AJ. If I just put an M for every single term, this is not a big deal, right? This is going to be increased by M. That's it. Nothing will be changed. But I need to do some magic from here, right? So what I'm trying to say here, okay, let me just try to rewrite it here. M plus AI, M plus AJ, right? If I add M, so the entire thing will not change, right? This is exactly the same thing. as AI minus AG absolute value, right? However, my goal is trying to prove that AI plus M, AJ plus M, if I can make sure original AI AJ, the greatest common divisor, is the same as AI plus M and AJ plus M, greatest common divisor. I can basically use all the equations, they can be passed along, right? So everything will keep the same. You guys follow me? So the $1 million question is that, how can I make sure this guy is the same? How can I prove AI, AJ, greatest common divisor, equal to AI plus M, AJ plus M? First of all, we're all on the same page. It can't be always true, right? M, if I am just 2 random values for M, this is not going to be true for sure. So that means I need to do some magic to narrow down the value for M. Like I said, all those constructions, M cannot be 1, 2, 3, 4, 5. It must be a combination between AI, AJ, between something you already know that can make sure your thing holds. Still remember? This is what I mentioned from day 1, right? M cannot be a real number, 1, 2, 3, 4, 5. M must be a dynamic number constructed using AI and AJ and make sure it holds eventually. Who can tell me how can I make some magic to make sure this guy is equal? M equals to 0. Like I said, no, you can't, right? M equals to 0, then narrow down, there's only 1. There's like nothing, right? M equals 0 means, right? At least M equals to 1, right? It means a little bit change. Again, if M is 0, that means there's only 1 M. But I need to create infinitely many M's. So M must be something magically you can figure out. What we are looking for is, I must be looking for an M to make sure this equation holds, right? The greatest common divisor of AI and AJ is the same as AI plus M, AJ plus M. I must find not only 1 M, I must find infinitely many M's. At least I need to find several M's, right? Let me give you a little bit hint like this. Because this is a very comprehensive problem. You need to be familiar with all the number theory things we talked about previously. Let me ask you, are you okay with this? Are you okay with this? What is this? AI, yes, somebody want to say something?
Oh, you're just subtracting the first thing from the second thing.
And this is what? Do you have a name for this?
No, but I guess it makes sense.
This is the Euclidean algorithm. So you have a very glory name, right? Euclidean algorithm. Are you guys familiar? I think some of you guys just went to the number theory lecture. Euclidean,
Yeah,
okay. Euclidean algorithm is AB. Greatest common divisor must be A, B, like the A and let's say B minus MA, right? And also A minus MB, M times B and B. This is the Euclidean algorithm to find out the greatest common divisor of 2 guys. For instance, I gave you 107, 27. This is 2 big numbers. I have no idea how to find out the greatest common divisor. I can actually use 107 times, I don't know, 4 times 27, right? 3 times 27, 3 times 27, and then 27. That's going to help you to reduce the complexity of your calculation. Okay? This is the Euclid. Okay, I'll write you the name. Euclidean algorithm. Euclidean algorithm. Find out the greatest common divisor. Okay. Because at our level, I assume that you guys know everything. So if you don't know everything, not a big problem. I'll give you the name. You figure out after the lecture. Okay. We're on the same page for this, right? What about this one? This is also this, right? Is it right? Again, I'm using Euclidean algorithm one more time. If I do a comparison between these two guys, who can tell me what's the value for m? Euclidean geometry means AB's greatest common divisor is A plus m times b, or k times b to make our life easier. Maybe you love k better. K times b and b. Who can tell me, if I give you these two expressions together, what kind of m you want to choose to make sure those two guys are identical to each other?
K is equal to A.
K is equal to A? No, not K. Here. This is only the Euclidean. I want to ask you here, what is the value for m?
0?
0. We go back to square one. 0 means the same, right? I need to find infinity many m's. 1 m is not good enough. I need to find millions of m's. M must be determined by using AI and AJ. Still remember? This is what I mentioned from day one.
AI,
M.
AJ?
Yeah? You guys agree with Joey? M equals to AJ minus AI, right? Or AI minus AJ, doesn't matter. Actually, not only AI minus AJ. As long as M is a multiple of AI minus AJ, you make the condition holds. Is that right? This is the challenging part. As long as AJ minus AI is a divisor of M, I'll make sure this two equation holds. Why? Look at here. From this guy to this guy. This is also a Euclidean This is also a Euclidean algorithm, right? At m equals to k, AJ minus AI, right? This is another Euclidean algorithm. Is it right? Huh? I'm actually writing it here. Why I'm writing here? I just want to write it here as a reminder to you guys. Do you guys agree with me? If m is equal to k times AJ minus AI, so this is actually another instance of Euclidean geometry. Not Euclidean geometry, Euclidean algorithm, right? A, B, greatest common divisor, A plus KB and B. A, B, A plus KB and B. So far, so good? Guys follow me? Yes or no? We're almost there. We're almost there. Okay, as long as AJ minus AI is a divisor of M, I can make sure these two guys are the same. So therefore, these two guys are the same. Is that right? You guys follow me? So therefore, AI minus AJ, absolute value will be M plus AI, M plus AJ. Is that right? But people will ask me a question. Oh, Alex, you spend so much time talking about so many weird things, but you're still giving me only m plus a1, m plus a2, m plus an, right? You still only give me m numbers. What I need is m plus 1 number, right? Is that right? You guys follow me? What I'm trying to do is find an m plus 1 number to make sure it holds, and my work will be done. Here is the magic. Here we'll kick in the magic. How to do from m number go to m plus 1 number. I'm just going to put a 0 here. Trust me, if I don't tell you, no one will know this. But this is the official solution. I'm going to put an m here. Because what I'm trying to do, AI, AJ, AI, my AI, oops, sorry. AJ, right? This is what I need. It works for m plus a1 all the way m plus an. So if I put a 0 here, nothing changed because we need to know the definition, right? 1 and 0, the greatest common divisor is also 1. 2 and 0, the greatest common divisor is also 2. This is a kind of like a definition. This, this is something that you know, and that's it. You guys follow me? So plus an m plus a 0, I will be able to figure out this guy, this m plus 1 numbers will also hold AI, AJ, AI minus AJ, right? So far, so good? Okay. That being said, that maybe you're not so happy with 0, right? 0 does not look like a so nice number, right? It doesn't matter. Think about it. We just proved as long as you have m number, I take m equals to AI, AJ, the greatest common divisor. I mean, like the multiple of AI minus AJ, I will be able to find out another number plus m. Then we'll make sure this number will exactly fit the condition. Is that right? Is that right? You guys follow me? This is what we proved before. Now, I'm looking at m plus 1 number. I will do exactly the same thing. m plus a1 plus n, m plus a2 plus n, all the way m plus an plus n. As long as n can be divisor of, for the original, oops. As long as I can make sure for those numbers, this is, I'm going to call it AI, big AI, big A1, big A2, big A3, to big an plus 1. I'm going to make sure AI minus AJ, right? N is a multiple of this. Then I will be able to construct such an n and construct such a n plus 1 number. You guys follow me this?
Yeah.
Oh, so that being said, my construction can be infinitely, right? Every time I can add n, every time I can add n. So 2016, it looks like this is just like a random number. You can put whatever number you like. This is actually infinitely many. This is a little bit crazy question. The crazy part comes from this. And you have to use what you just proved out from n to create n plus 1. And you can keep doing that forever, forever, forever. So far, so good? Any questions? Again, don't struggle for the super detailed things. Understand the big direction. This is the big direction. We're going to use the inductive construction is trying to do this, right? From from n to n plus 1, from n plus 1 to n plus 2. So that being said, if Alan can tell me a1 equals to 2, a2 equals to 4, I will be able to create a a1, a2, a3, right? By using the m. And then I will be able to create a1, a2, a3, a4 by using an n. And then so on and so forth. I can basically do this as many as possible, right? And James, you can try to figure out your 2n minus 1 thing, it is working or not, because I don't really check it. Think about it, if that one. But I don't think it can be derived from here, but maybe there's another correct solution. If you have it here, then we don't have to go for this. Right, I think that's pretty much what I want to say for the entire construction method. A quick recap. We started with the inequality, right? Inequality is actually a very big thing we do the construction. Most of the time we're using the graph. And then moving forward, we go to like the sequence related problems, right? And then today we focus on we'll focus on the number theory. Number theory has two parts: the regular number theory problems, as we are talking about for now, or the Delphantine equations, as we talk about at the very beginning. So just like this is like the beauty of construction. And the most important thing is you understand the common strategies we introduced during the construction method. Okay, so later I'm going to give you guys some problems as a homework. So normally I will give you the homework tomorrow. I'll let you guys think about it for today's lecture. And then from tomorrow, I'll give you the assignment. You have 2 weeks to finish your assignment. Again, for this lecture, you're not supposed to know every single problem and solve out every single assignment. My goal for this lecture is to help you guys expand your horizon, because this problem is more like if you only go for the AMC, like like Euclid or something, you won't be able to see these questions. So it just only helps you expand your horizon. If you go to some high-level math competition, CMO or something, you will be able to see this problem in the daily basis. So this is like a training. There's a big gap. All the AIME training and all the CMO training, there's actually a big gap in between. And even like the Euclid question number 10, sometimes is also very difficult as well, right? So there's a gap in our regular day-to-day training. So we're just trying to help you guys bridge the gap, how to find out these weird but still understandable questions to solve it out. Sometimes the Euclid question number 10, we're going to use maybe 35 minutes to do one problem. I don't think it's a good problem. Sometimes these problems, we only use 20 minutes, but you never stop thinking for this 20 minutes. Every single step, you need to follow I need to drag you. Come here, come here, come here, right? This is like the difficult part. All right, so I think that's pretty much what I want to say for today's lecture. Have any questions for the next unit? Let's go for let me check my next unit, because we have a bunch of actions. We have a bunch of topics. I want to find out something which is more which is more related to you guys at this moment. I might go for the proof by contradiction, or I might go for the squeezing method, squeeze out method. Let me think about it. Maybe I'll give you the proof. I'll give you this like the forecast, okay? A preview pretty soon. Okay. Any questions for me? All good? All right. In that case, I'll see you in next 2 weeks. All right. Bye, guys. Ciao, ciao.